Good morning, everyone. Welcome to a full day of addressing the climate crisis through the practice of architecture. Katie, Adina, thank you for inviting me to speak today. It's an honor to take part in this climate symposium, especially in New York, my home state, an early adopter of low-carbon construction policies, which are now focusing on embodied carbon. Perhaps second only to California. California was the first state to initiate embodied carbon policy and legislation, the Buy Clean California Act back in 2017. New York State's Climate Act, which included emissions associated with manufacturing, cement, and the building sector, became law in 2019. Reducing the built environment's contribution to carbon emissions actually begins with raw material and manufacturing emissions, the upfront embodied carbon. Many years ago, when I first started my engineering career, designing sensors for the space shuttle program and various defense projects, the phrase embodied carbon was not yet a part of the English lexicon. Yet today, it plays the pivotal role in sustainable design, a pivotal role in global warming. Embodied carbon and embodied emissions might be the most poorly named concepts in the global warming vocabulary. There is nothing embodied about embodied emissions. By the time we refer to them, they have already been released. They do not exist in the material or the product in question. This beautiful sky is what embodied emissions look like, residing in the atmosphere as atmospheric carbon, not visible to the eye. They will remain there for hundreds of years. But they are there, multiplying the greenhouse gas effect. Water vapor is also a greenhouse gas. Water vapor and stratiform clouds contribute nearly 3/4 of the heat re-radiation, 3/4 of the greenhouse effect. Carbon dioxide is just 20% of the greenhouse gas mix. Though only 20% of the mix, carbon dioxide's greenhousing effect controls 80% of the impact. Heat re-radiation from atmospheric CO2 increases air temperature, which in turn influences the air's moisture content. But unlike water vapor, CO2 neither condenses nor precipitates from the atmosphere. It stays there, re-radiating heat and enabling higher levels of water vapor, which do so as well. This nebulous thing called embodied carbon is one of the few warming accelerants that we can minimize within this decade, something that everyone in this room can do. What are embodied emissions? That depends on your perspective. To some, it's manufacturing emissions, the emissions associated with producing a product. That means from raw material mining through production and packaging and everything in between, from cradle to the shipping dock. To others, it includes transportation to the construction site, or maybe installation or maintenance, or repair or refurbishment, or disassembly and disposal, or preparation for eventual reuse. Is embodied carbon important? New York State's Climate Act thinks so. Named the Climate Leadership and Community Protection Act, it started New York's ball rolling. In 2021, New York State passed the Low Embodied Carbon Concrete Leadership Act, a very long name. In 2022, the Climate Action Council released the Climate Act Scoping Plan, which includes market development and incentives for low embodied carbon products and construction. New York State Executive Order 22 and New York City Executive Order 23, both issued in 2022, they both address embodied carbon. The Inflation Reduction Act, the IRA, put $4.5 billion on the table for low-carbon construction materials, perhaps because embodied emissions are immediate and unrecoverable. Between now and 2030, as much as 70% of carbon emissions attributed to new buildings will come from embodied carbon. Unfortunately, none of this has been promoted. With 2030 targets a mere 5 years away and a climate crisis brewing, minimizing emissions up front is crucial to the 1.5 degree target. Even though the AEC industry has worked diligently to obtain energy efficiencies, to employ energy modeling, electrification, and energy decarbonization, and to design more net zero buildings, we need to take stock of what we refer to as sustainable design, stock of its veracity regarding emissions, stock of reality. Building designs come to fruition within the architectural professions. Whether you are an architect or a designer or an engineer, a client or a builder, or part of the construction industry, be it a building or infrastructure, an interior, or the systems, fittings, or furnishings, your project's contribution to atmospheric carbon begins with embodied carbon, upfront embodied emissions. Whether by design, by specification, or procurement, every element of the construction process arrives with a prior release of embodied emissions. So how are we doing? Are we minimizing greenhouse gas emissions in a timely manner? Does our progress reflect building design? Or is it coming from equipment and appliance efficiencies? Or is it primarily from energy decarbonization? Is our current approach to sustainable design enough to thwart global warming? I've spent more than a decade investigating the built environment's impact on our surroundings. The last 6 years exclusively on embodied carbon's role in global warming. So much time that my wife, who's an urban planner in New York City, forbade me to mention embodied carbon or even EPDs during mealtimes. Truth be told, preferably not at all. Well, I'm sorry, Paula, even though you're not here, but today there were 6 AIA learning units. So without apologies, let's begin. There's this thing, there we go. Let's turn the calendar back to 2018, a year that set the stage for New York State's Climate Act, as well as New York City's Local Law 97, both becoming law in 2019. I was researching THWART Climate Change Now at the time, my book about embodied carbon. That December, as one of COTE's 10,000 members, I received an email, a post to COTE's website. I remember it to this day. It began, quote, "Happy holiday, this is big." It explained that amid sobering projections about climate change, there was some upbeat news to share. Quote, "Our hard work is having a big impact," it said. Our hard work caught my attention. The post stated that energy efficiency and power sector decarbonization have reduced U.S. building sector CO2 emissions by 20.2% below 2005 levels, and this was 2018. And this was despite adding approximately 30 billion square feet to our building stock. At first glance, I thought, wow, our work is having a big impact. Sustainable design must be working. But reading further, I realized this upbeat news, based on an Energy Information Administration report, was attributed primarily to energy efficiency. and to power sector decarbonization. So what part of that was due to our work to designing buildings? Parsing the data, the minutiae, was like opening Pandora's box. The 20% reduction was real, but had little to do with building design. The significant reductions came from replacing coal with natural gas, wind, and solar, and a notable reduction in the energy used for illumination, from compact fluorescent lighting, from the introduction of LEDs, which perhaps was the most significant contribution to lowering operating emissions since 2000. But there were other factors too. Energy demand had decreased due to mild weather and to poor economic conditions. One might say that emissions declined in spite of new building designs. But there is something else to note here. EIA's building sector only included emissions from the residential and commercial use sectors, and only their operating emissions, such as heating, lighting, air conditioning, and electricity consumption, not embodied emissions, the ones released up front, not from manufacturing the construction materials, nor the fittings, fixtures, and furnishings, nor manufacturing the building systems or appliances, nor from the transportation of any of these items, nor manufacturing the construction equipment or vehicles or operating them. In other words, due to how economic sectors were categorized, the magnitude of emissions attributed to buildings was significantly higher than reported. This is what I mean by taking stock of reality, the veracity of the claims, and the efficacy of our actions. Since 2018, our understanding of sustainable design has changed. We've learned that not all carbon emissions have the same impact on the rate of global warming, that upfront embodied emissions associated with the production of construction materials accelerate global warming. They add fuel to the fire. They play a defining role. Embodied carbon is the elephant in the room. Since 2018, we have built over 250,000 privately owned housing units in New York State. And that includes during the COVID shutdown. More than 1 million units in New York State since 2000. Last year, nearly 50,000 new building permits were issued in New York State for residential units alone. Here we are closing in on 2025. Everyone is reporting about 2024's record-breaking heat. July was the 14th consecutive month of record-high global temperatures. No one talks about the record-breaking level of the atmospheric carbon that causes them. We are still being fed green platitudes and pats on the back and regurgitated statements based on a paucity of verified information. We are still talking about policy, about data collection, and mandates, not action. But action is possible by everyone in this room. According to the hidden climate impact of residential construction, a recent report by RMI, cradle-to-grave embodied emissions from new home construction could exceed 50 million tons of CO2 equivalent gases annually. This is just for U.S. residential construction. According to the study, up to half of those embodied emissions can be eliminated with commercially available, affordable, and code-compliant building materials. As much as 75% reductions are possible with one-to-one material substitutions. Reductions like this are available in all phases of construction, and all of this starts with an architectural design. The power to reduce those emissions resides with all of you. It simply requires your sensitivity to embodied emissions, plus some creative thinking. In other words, relating spatial, structural, and envelope design to material selection while cognizant of embodied carbon. The same is true for fittings, fixtures, and furnishings. We need to realize that sustainable design commences with low carbon construction. Some of you might ask, with wind and solar and electrification on the rise, why this sudden emphasis on upfront emissions? To answer that question, let's cut to the chase. Let's connect a few dots. Let's look at carbon emissions and the warming timeline. The blue line here traces the increasing concentration of atmospheric carbon in ppm, parts per million, from pre-industrial through 2023. In 1910, for the first time in over 300,000 years, the concentration of atmospheric carbon exceeded 300 parts per million. A new daily record exceeding 428 parts per million was reached on April 26th of this year. An increase of 128 parts per million over 113 years. The rate of increase since March 2000 is double that, 58 parts per million in only 24 years, 53% higher than the prior 24 years. Unfortunately, atmospheric carbon is the factor that induces global warming. For the 2,000 years prior to 1900, the average temperature stayed within plus or minus 1/4 of a degree Celsius. Since the early 1900s, it has increased more than 1.3 degrees Celsius, and that's the red line on this chart. According to NOAA, the National Oceanic and Atmospheric Administration, 2023 was the warmest year since global records began in 1850. The average global surface temperature for 2023 was 1.35 degrees Celsius above the pre-industrial average, the Paris Agreement baseline. I created this graph in March for a keynote at LA's COTE Symposium in April. This is what it looks like now, updated through this August. A bit shocking. The average for the 12 months through this August was even higher, 1.49 degrees Celsius above pre-industrial. We've continued to break global temperature records each month. These increases were driven by the increasing concentration of atmospheric carbon dioxide. Temperature increases are nearly linear now with the increase in atmospheric carbon. The concentration of atmospheric carbon is driven by carbon dioxide emissions released from fossil fuels and industrial production. That's the black line on this graph, in billions of metric tons per year, gigatons. The red circle reveals the reduction in annual emissions in 2020 due to the COVID shutdown. The COVID dip in the black line here is considerable, a reduction of more than 2 billion tons of carbon emissions for that 1 year. But notice the blue line, the level of atmospheric CO2. It continues to climb. Why? Because CO2 emissions remain in the atmosphere. They are not reduced as emissions decrease. New emissions are additive. They will remain in the atmosphere for centuries. To flatten the growth rate of atmospheric carbon, we must reduce emissions now, annually. Unfortunately, as you can see from this graph, annual emissions, the black line, have already returned to their pre-COVID level and continue to increase. And unfortunately, though we are well on the way to decarbonize our energy supply, demand for energy is also increasing. Worldwide, increasing faster than decarbonization with no net gain. This drill on climate science is is to make a single point: the urgency of tackling upfront emissions. What we spew into the atmosphere today and tomorrow will increase global warming immediately. This is why upfront embodied emissions are so egregious. Waiting for the 2030s or for future decarbonization to start flattening the curve is wishful thinking. Regardless of all the green certifications, fawning articles in the press, and competition award winners, we are not doing enough. It comes down to efficacy, the effectiveness of our attempt to design sustainably. Excess embodied emissions are not a necessary fact of life. They are designed in by structural, material, and aesthetic decisions, some even in the name of sustainability. To provide a little context for today's symposium, let's focus on a few building designs, ones that highlight what I'm talking about: embodied carbon, the upfront kind. This is the new design studio at the University of Miami's School of Architecture, completed in 2018 and LEED certified. The 20,000 square foot roof with its 5,000 square foot overhang was constructed from reinforced concrete. Embodied emissions estimate at more than 100 metric tons of CO2, in addition to those from the building's concrete walls. We all know that cement is responsible for 8% of the world's energy-related CO2 emissions. I hope architecture students learn that as well. It's not that cement concrete was used, but rather the overabundance, the quantity. What were they thinking? Should this be a model for architecture students to emulate? This 62-story residential high-rise in Miami was completed in 2019. The exoskeleton was clad with 4,800 precast glass fiber reinforced concrete panels, weighing a ton or more each. They were shipped from Dubai, 9,000 nautical miles and dozens of trips. CO2 emissions from concrete cladding might be deemed excessive by itself. But shipping from Dubai to Miami, emitting hundreds of thousands of kilograms of additional CO2 emissions. On top of that, they were shipped with custom steel cradles for protection, adding significantly to that embodied carbon. What were they thinking? This beautifully conceived LEED silver project with geothermal wells for heating and cooling was completed in New Canaan, Connecticut in 2015. For part of the structure, they chose glulam beams, environmentally sustainable, a great carbon sequestering choice. But perhaps, I must add, the LEED certification for building design and construction noted the use of green building materials. But perhaps their point of origin was not part of the equation. The glulam beams were fabricated in Vancouver, British Columbia. The project about an hour south of here. Some beams were as long as 95 feet, unsuitable for transport on winding roads. They had to be trucked by a route around the Rockies from British Columbia almost to Mexico, then up and across the US to Connecticut. Around 20 truckloads responsible perhaps for 250,000 kilograms of CO2 emissions. Even environmentally conscious design can be undone by transportation. Oh, how about those full-height glass panels? They were manufactured in Germany. Then they were shipped to Spain to be curved before coming to Connecticut. Sustainable design? What were they thinking? This computer science building at Cornell University, my alma mater, was finished in 2014, a glass-clad structure with steel sunscreen appendages to block heat-inducing sunlight. This is the north side of the building. According to Cornell's Sustainability Office, these angular sunshades contributed to the structure's LEED Gold certification. Nonetheless, the intense sunlight from the east and south necessitated additional interior pull-down screens to screen the exterior screens. And you can see that, that's the photo on the right. Why one would design a computer lab with floor-to-ceiling windows that admit the sunlight and glare, I'll leave that to you. But it's hard to ignore addition of steel sunscreens on the north side of a building in the northern hemisphere. Steel emissions are in the same league as cement, responsible for about 8% of global energy-related emissions. Was this just for aesthetics in the name of sustainable design? What were they thinking? What about solar panels? Do rooftop solar installations generate enough energy to justify their embodied carbon footprint? Not this one in the Hudson Valley, shaded by trees. I hope none of you own this house. See. It may reduce the homeowner's electric bill, but this one is a net negative for carbon emissions, probably for its first decade of operation. And this is not uncommon. Here's another one in the Bronx with panels oriented to the north. Perhaps these residential examples were directed by the homeowner. This array, however, is attributed to architects. It's in New York City's Washington Square Park, amidst tall trees and tall buildings, installed in the name of sustainable design. What were they thinking? Not all rooftop solar installations justify their embodied footprint. Southern regions in the U.S. receive sufficient irradiance, but northern states have 10 to 25% lower solar exposure. With shade from buildings or trees or poor directional alignment, they will actually add to global warming for a long time. For all of these projects and numerous more like them, the answer to what they were thinking is simple. They were thinking about fluidity of design, in some cases, perhaps sustainable design. You know, the thermal mass of concrete, carbon sequestering wood construction, the benefit of sunscreens, and why not add solar panels? But they weren't thinking about embodied carbon, about upfront emissions. So let's focus now on you, the professionals who design and construct our buildings and infrastructure. Let's borrow a phrase from our Department of Homeland Security. If you see something, say something as early in the design process as possible, before it gets baked in. Today's discussions will address strategies to minimize carbon emissions and to address their impacts. Please keep in mind that at every stage of design, we need to question its global warming potential, from conceptual to structural to envelope design to fittings and fixtures through material procurement. A few key factors that impact upfront emissions are a good place to start. Whether it's material selection or substitution, structural strategies, circularity or reuse, or material conservation, when embodied emissions are in mind, excess materials, poor choices, and transportation emissions become obvious. And your ability to predict the efficacy of your designs will rely on a few simple factors. First and foremost, how much of a product will you use? The second, what is the product's global warming potential? It's GWP. It's CO2 equivalent emissions per unit of use. And third, as I've demonstrated, where is it manufactured? GWP and point of manufacture can be found on a product's environmental product declaration. It's EPD if it has one. which brings us to the Achilles heel of low-carbon design, EPDs. Addressing a materials abundance or use of long-distance shipping is obvious, but trying to compare the emissions from one design scheme to another with EPDs, or comparing one vendor's products to another's, is something else. How many of you have actually used EPDs? Show of hands. 2. Okay. Well, maybe I caught you in time here because I'm going to tell you a few things about them. If you've tried but couldn't find many, you're in a majority. Nonetheless, they will become obligatory. How many of you are familiar with New York State Executive Order 22? Again, only a few. It covers new construction, 5,000 square feet or more, or significant renovations for New York State agencies or departments under the governor's authority, which includes universities. The exception is the Port Authority. Permitting requires that design teams calculate total embodied carbon, including from shipping and for transportation and construction equipment. Bidders are required to submit EPDs when available for covered products. Executive Order 22 has been in effect since January 2023. New York City followed in similar fashion with Executive Order 23, requiring submission of EPDs for concrete and steel to Building Transparency's database. EPDs are also required for IRA funding and Buy Clean programs. And this is only the beginning. To evaluate the global warming potential of any manufacturer's product for any of your projects, you must rely on its EPD. Unfortunately, the availability, reliability, and comparability of EPD data is severely lacking. Aside from ready-mix concrete, there is a paucity of EPDs to survey and little geographic distribution. For those that exist, there lacks a single rule set to support comparisons and certainty. EPDs must conform to what's called product category rules, PCRs. But multiple PCRs may be issued for a given product category by different groups of interested parties. And optional formats may be allowed by a single PCR. Here's an example. If you haven't ever used these, it may be a little confusing and it's probably hard to read. This declaration, these are first 2 pages from an EPD for ready-mix concrete from a plant in Westchester County, issued on August 8th, and it's valid for 5 years. It was created from the latest rule set, the PCR for concrete from NSF International of February 2024, version 2.3. The mix has a compressive strength of 3,000 psi at 28 days. It's important to note on page 2 that this EPD was calculated using manufacturer-specific cement data. And that's the way that it should be, which is detailed in the list of sources. This declaration is from another EPD for a 3,000 psi mix at 28 days from a different Westchester County concrete plant. It was created from the exact same PCR using the same third-party verifier and published within a day of the other EPD. Both of these are in Building Transparency's database, the one required by New York City. Yet they differ in their disclosure certainty. This one comes with a huge caveat. While the prior one was computed using manufacturer-specific cement data, this one used industry average data provided by the Portland Concrete Association. As such, the GWP value declared on page 1 is modified by a caveat, a disclaimer, on page 2. It states that the manufacturer-specific cement impacts could result in variation of as much as 37%. That's because they didn't use manufacturer-specific cement data in this EPD. In other words, the GWP declared on page 1, the 254 kilograms of CO2 equivalent per batch, might be inaccurate by 37%. In fact, they don't tell you whether that's plus or minus. A caveat like this renders this EPD meaningless. You wouldn't know that if you just took the data from the database, unless you actually printed out the EPD itself and read all the fine print. Fortunately, with the recent scrutiny of BiClean programs, more EPDs now use manufacturer-specific values, but nonetheless, New York State has a long way to go. Close to 80% of New York State plants that entered or updated EPDs in Building Transparency's database in the last 6 months through September submitted EPDs with this kind of caveat. And keep in mind, nothing requires EPDs to be comparable from manufacturer to manufacturer, even from different plants of a single supplier. The EPA is working to change that by developing a registry for low-carbon construction materials that meet IRA standards and to make them accessible online. Hopefully these programs will be viable, but they will take years to facilitate and to gain traction. So until a sufficient supply of standardized EPDs are widely available, what can you do in the meantime to cut upfront emissions? How does one attack this problem? The answer is by focusing on what you can control. There are 3 phases to the accrual of embodied emissions in a product's life cycle. The first phase, from raw materials to installation, is known as the A block. Then comes the use period, the B block, maintenance, repair, and replacement. Finally, the C block, end-of-life emissions, deconstruction, transport, waste processing, and disposal. If circularity is part of the discussion, there is a 4th phase, the D block, recovery and reuse. All of these are important, but our immediate goal is to reduce upfront emissions. That's the A block. What occurs past the A block, past installation, is speculative. More speculative the further out you go. Speculative about use, maintenance, repair, and replacement, especially about a building's lifetime, or whether components will be recycled or reused, or whether embodied carbon will even matter then 40 years from now should zero carbon energy dominate the grid. To some extent, full life cycle modeling may be spinning wheels for at least now. Life cycle A block emissions are tangible, controllable in real time by your design and procurement decisions. Focus on your A block decision making. What about circularity, the potential for reuse? Am I saying don't bother? Absolutely not. Circularity is extremely important for many reasons, even if a particular component is never reused. Designing for ease of disassembly or reprocessing is a carbon benefit, and it may be designed to minimize waste, pollution, and landfill, all environmentally beneficial. Nonetheless, having low upfront emissions is critical for circular products too. Modeling is crucial to sound design decision making, from structure and envelope to environmental control systems, and a host of other parameters. How do we handle the EPD problem? Modeling and detailing are at different ends of the spectrum. That's if you model to design rather than model what you've already built. Industry or manufacturer average EPDs or database averages are sufficient for modeling design schema comparisons. whether for the structure, envelope, or interior. A GWP estimate for modeling can be determined from most EPDs, even for those which may seem somewhat misleading. Just be sure to factor in the caveat. Comparing design approaches can be accomplished with generic information, but detailing is another matter. Ultimately, success or failure of a low-carbon project will be cast by the structural and aesthetic decisions carried out through detailing and locked in by a spec writer. And that's when emissions comparisons become critical, ultimately relying on the veracity of specific EPDs. Until we have a sufficient supply of EPDs and widespread comparability, low-carbon design will rely on your creativity and your skill sets, your design and material choices. So I will close with a few rules of thumb and a few thoughts that can help. Rule number one is the easiest way to cut embodied carbon. It's a throwback to Mies, less is more. No matter what material you select, less of it is more climate friendly. Embodied emissions come by the pound or kilogram, or by the unit or square foot. For example, a 50-pound bag of cement already emitted about 40 to 45 pounds of carbon dioxide during production. Of course, material reuse or circularity, or increasing a building's lifespan by renovation or adaptive reuse, serves this credo as well. Rule number two, be cautious with products processed at high temperature. Firing ceramic, porcelain, and brick, sometimes multiple times, for surface effects, to create color, or a shade of black, or for glazing, adds emissions. Thanks to this helpful disclosure from a brickmaker's EPD, one can see the emissions impact of an aesthetic choice. There is a 21% spread in upfront embodied emissions from color groups 1 through 10 of this particular manufacturer's bricks. Your choices matter. Rule of thumb number 3, check a product's material content. You can't tell a book by its cover. Many construction products are composites of materials, such as for roofing and siding. The principle of mass applies here too, the mass of high GWP constituents. Of course, whatever the product, let's not forget transportation emissions to the construction site. But if you can only handle one of the above, make it rule number 1, use less. At COP28 last November, UN Secretary General Antonio Guterres noted, it's minutes to midnight for the 1.5 degree limit, but it's not too late. He was referring to the temperature increase above the Paris Agreement pre-industrial baseline. How close are we? What is the urgency? That relates to where you get your information and to your attention to the details. If you read the Wall Street Journal on September 24th, this front page graph implied we are roughly at 1.25 degrees centigrade, well below the 1.5 degree target. But looking at the details, the temperature increases plotted relate to the 1961 to 1990 average temperature, not to pre-industrial. I have no idea what the purpose of this was, but that was on the front page of the Wall Street Journal. If you looked at NOAA's website for the 12-month period ending this August, 1.32 degrees C was reported. But that was above the 20th century mean, not pre-industrial. When that is adjusted to the Paris Agreement baseline, the result is an increase of 1.49 degrees Celsius, so basically 1.5. And that was for the last 12 months. If you look at the EU's Copernicus Climate Service, which you don't see very much here, it was reported that global surface temperatures had reached or exceeded 1.5 degrees Celsius above pre-industrial for 12 consecutive months. So we have choices. We can ignore the details, comforted by our faith in the press, and we can install green appendages to please a client or as a feel-good green. Or we can meet the letter of new building codes and new climate regulations rather than the spirit. But none of this will reduce carbon emissions soon enough to make a difference. We must take it upon ourselves to act. I came across an excellent report that might help, published by the World Business Council for Sustainable Development. Net zero buildings halving construction emissions today. The report provides excellent strategies to reduce embodied carbon. It's available for free download at wbcsd.org. I highly recommend it. For a more complete picture of the mindset we need going forward and how our love affair with all things green and sustainable got us here, my book might help. Thwart Climate Change Now, Reducing Embodied Carbon Brick by Brick. I wrote it to be a solutions-oriented eye-opener. It comes down to our creativity, to our personal decisions. With approximately 120,000 registered architects in the US alone, about 3.2 million estimated worldwide, we can make a huge difference. And that doesn't include interns or other design professionals and the rest of the AEC industry. This is an enormous amount of specification power, capable of minimizing upfront embodied emissions through low-carbon construction. Keep in mind that embodied emissions from construction materials are released years before a building is ever occupied, years before infrastructure is ever used. That is why your ability to cut upfront emissions through design and by material selection matters so much, why it is so important. And to quote a rapper, not that I follow rappers, but an activist, Robert Banayan, was interviewed by the New York Times. He was working to create low emissions music festivals. He said, if it's not 1.5 compatible, it's irrelevant. Simply a gesture, an idea. It's not doing anything. So let's get to work and let's spread the word. And please don't forget, if you see something, say something. Thank you for listening.
Thank you, Katie. It's good to be here. Great to see everyone. Nice to see some familiar faces and a lot of new faces for me. So I hope to meet you later on today as the day goes on. I should also note that speaker this afternoon and significant person here, Bruce Becker, recently became, there you are, Bruce, I'm looking around. Bruce recently became a board member of the Passive House Network, which we're very proud of. So I have to give this presentation my best effort or I'll be in trouble. So I named this presentation, it's an introduction to Passive House, that anyone can build a passive house. I think people think about passive house or first hear of it and it's like, oh, we're gonna build a spaceship. I need to be a super engineer. I need to be able to deal with super complicated things. And really, anyone can do it. It's about intent. It's about a few simple principles and following through. Myself, just briefly, I know the bio, but I did practice architecture for a couple of decades. I had a small firm in Brooklyn, New York, did mostly retrofits of townhouses, and you'll see at the end a townhouse that I did, which really got me into Passive House as a professional. I'd seen An Inconvenient Truth, and was in a climate panic back at that time, and was really looking around for a way to apply what I did as a professional to the climate. And really feeling like all the sustainability programs that were out there had a lot of good attributes, but I couldn't connect the dots and see where the impact ultimately was. And then I came across Passive House one day in 2009 and was like, had this aha moment and was like, oh, we can do this and we can really have a significant impact. And was able to convince some early clients to do it, in which I'll bring up this story a couple of times along the way because I think it helps illustrate the power of what we're doing. We can skip that, so we'll talk about why Passive House, the logic, the methodology, the tools, some examples. I will note, we as an organization, the Passive House Network, we're affiliated with the Passive House Institute in Darmstadt, Germany, and the International Passive House Association. One of the things that appeals to me personally is the global aspect of this effort, and we learn from people all around the world, all across the state, across the country, in different climates and so forth. I know there are a couple of flavors of Passive House. 99% of what I'm going to say is totally transferable between the different certifications, but I do want to speak to what I know of. So I think, and I must commend Bill for his presentation earlier. It was amazing and inspiring, if a little scary, which I think is intended to be. And I wanted, Perry, his presentation to say, yes, and. Everything that he is presenting is true. We need to tackle the upfront carbon is absolutely crucial. But there's more architects have power over. And we need to not let ourselves off the hook with one aspect or another. So I like just the saying that building is not a neutral act. We're going to be helping things get better, or we're going to be helping things get worse. We can't pretend like it doesn't matter what we do. And I don't think architects feel that way typically. They just maybe don't embrace it with the intensity that it could deserve. So we spend a lot of time indoors, global emissions, and fundamentally with our buildings, although the codes are getting better, certainly as Bill was speaking to, the different efficiency standards that are out there are improving, if painfully slowly. At the end of the day, bringing the building together is such a complicated act, and the ultimate performance of it can be quite unreliable, And so we have our engineers oversizing mechanical systems as a perfect illustration. Nobody trusts that the building will actually operate the way we think it will operate. They tend to run more expensive than we think. They can too often be unhealthy to the occupants and exacerbate inequality as we see the disparities in investment in our physical structure and everything that happens around that. So all items to be addressed. And we really do want it to start with the occupants. I liked the upfront talk by Josh, about human resilience as being a key part of this in human health. And our buildings are a big part of that. And so basically, we're going to have two types of buildings. Buildings that are prepared for climate change, buildings that are helping mitigate and adapt to climate change, and those that are not. And so one of the themes that we have is to future-proof our architecture. We want to build something today, and we can do it, that will last through the coming decades, which are going to be quite harsh. And I think an interesting thing for me in getting into it, and I think for many, is that Passive House is focused on energy efficiency as a driver of building performance. But there's a realization that efficiency wasn't necessarily about sacrifice. It wasn't really about settling, which we can sometimes think of it as. It really can actually drive fundamental performance. So things like comfort and bringing down emissions, having health, sustainability, lowering risk. All of these things are goals that we want out of all of our projects, right? And efficiency can actually help us get there, and passive house as a methodology, which we'll dive into. Another aspect that excited me as an architect, I see it with other architects and builders and everyone in the projects, is that it's empowering the architecture again. You know, before World War II and the advent of mechanical systems that could compensate for really terrible building enclosures and generally building the design that disregarded the environment around us, you know, there's a tradition of vernacular architecture and medieval, ancient, indigenous architecture that engaged fundamentals. And it allows us to re-engage those fundamentals. It empowers the building elements first before we go to the mechanical systems. It gets us back into the details. We'll talk about how we're really using the same bricks and mortar, and we'll talk about the upfront carbon a little bit. But you know, how are we using those things? So it's putting, I would argue, the power, more power back in the hands of architects to use the structural design, the enclosure design, the form to drive the final performance of the building, and the builders along with it. And in power electrification, we hear a lot about electrification, renewable energy production. The fundamental issue with our status quo, moving to electrification and moving to renewables, going towards a net zero home, is that our demand and production are not in sync with each other. They are inefficient in how it's using the power. So our typical building, do I dare touch this? Which one is this one? Yes, here we go. So our typical building, this red line is the demand. And we see in an all-electric building where the heating is now electric, the demand in the winter is going to be way up, where our renewable generation is at its lowest. As we're overproducing. We may net zero out on a calendar year, but it's not actually producing the energy when we need it. So we have massive long-term storage losses, theoretically at least, in terms of what balancing out the system. Whereas in a passive house, we're looking to tune the system so we're not eliminating heating or cooling needs, but minimizing them and closing that gap. We can lower the electric renewable production and kind of tune it to the future renewable grid. Because today, this is from California, hopping back and forth, but indicative enough that space heating is really dominated by fossil fuels, right? Hot water also is as well. And so as we move this towering demand over to electricity, what are the effects that it's going to happen? Now, Massachusetts has recently mandated, they've moved away from EUI, and not get into it in too much detail here, but they've mandated what is called TEDI, Thermal Energy Demand Intensity. And it's basically the heating and cooling of the building is what's going to drive their building code for commercial and larger buildings. And multifamily buildings, for the jurisdictions that adopt it, passive house certification is actually becoming a requirement for multifamily over 12,000 square feet. That's one hell of a thing for a state to do and to regulate, especially this. I mean, it's late, as Bill pointed out, but it's still early in some ways in terms of adopting this for the industry. And so briefly, if you have the model code today, the summer is the electric peak. There is no winter peak because the heating is used for nothing. This is a school example that I'm using. There is no winter peak. When we flip over to model code with all electric heating with heat pumps, the cooling peak stays the same. It may go up a little bit as the weather gets more intense, but the winter peak goes off the charts. And Massachusetts infrastructure is not prepared for this. Nobody's infrastructure is. They're looking at tens of billions of dollars of investment just to get through the next decade. So what they see with Passive House in crushing the heating demand is a grid-friendly way to develop buildings going forward. It's actually an investment in the grid through better building. And we compare what we're going to be talking about in investing in efficiency, the structure of the building, to net zero. Net zero can be absolutely makes sense, but as a kind of like construction as a goal by itself, it could be incredibly problematic. So this is the ASHRAE headquarters, which is supposed to be really energy efficient, you know? And they had to cancel out half of their parking lot, or guess what they weren't using, with solar panels, and just, you know, to the horizon, let's have solar panels to make up for the supply. So it's focused on supply rather than demand. We're going from fossil fuel production to renewable production. It's the wrong side of the equation. We need to reduce the demand. Net zero also will favor low-rise buildings, because it's very hard to get a net zero building that's over 4 stories, perhaps. So why are we penalizing higher density? And it can encourage more inefficient land use and a false sense of accomplishment, we might argue, unless you've actually figured out the right balance for it. So I'm not here to rail against net zero per se, but to say that some of the common kind of like conventional received wisdom in terms of how the market is moving and what people are thinking for and asking for, like if the client wants to have solar panels on the building, we're going to end up with solar panels on the building, but we could have a wider conversation about that. Addressing embodied carbon is hugely important. Upfront carbon, in particular, as Bill pointed out, from the manufacturer to the installation. What we have in Passive House is a tool called the pH ribbon, and it is pulling from the EC3 Building Transparency Database, so the information is as good as what is being supplied. But you can actually look at the embodied carbon outputs of the building design along with the operational energy, so you're getting a more complete picture. And we can do, I think one of the key aspects of what I heard earlier was this material substitution, right? We want to use less. Less is more, but also substitute materials. We can add more insulation if the insulation is actually zero emissions, or could even be negative emissions, and help at the end of the day with the overall carbon profile. So something to consider. This is not core in Passive House, but it's not Passive House practitioners, because they are doing it out of mission of climate often, as well as a bunch of other benefits we'll talk about. Upfront carbon concerns are a natural pairing with it. And we want to note that it works with all the other codes and standards. You don't need to pick and choose. You can pick and choose as you like. This is the Winthrop Center Tower in Boston that was completed the other year. The world's biggest certified office building, over 800,000 square feet. And they did LEED Platinum and WELL, as well as Passive House. So we want to look to that. Blending, whatever makes sense for your project. So this is the heart of it, in a way, is like what Passive House does in transforming it is like we've got basic ingredients of building, light cooking. It's how we use those fundamental elements that really matters. And I really like this book, Salt, Fat, Acid, Heat. So if you know how to manipulate and use these basic elements of cooking, you can make a great meal, no matter really what is getting thrown at you. You know how to bring that out of the ingredients for the food. And the situation that we have in building is very much, I think, encapsulated by Wolfgang Feist, who's the founder of the Passive House Institute, has a quote that, I was working as a physicist. I read that the construction industry had experimented with adding insulation to new buildings and that energy consumption had failed to reduce. This offended me. It was counter to the basic laws of physics. I knew that they must be doing something wrong, so I made it my mission to find out what and to establish what was needed to do it right. And that's not surprising, right? Here with buildings, folks are doing buildings, but they're undermining one really good aspect that they're doing with something else that they're doing. So they may not be lowering, they may not be reaching the goals that they're seeking. And so Wolfgang doesn't know. I'm comparing him to Chef Cousteau from Ratatouille. But it really is this idea that anybody can cook if you have the basic knowledge, and anybody can build a passive house. And we're going to walk through that methodology that makes it possible. One more stop along the way, the basic definition, which is all part of this process of transforming our expectations, transforming what we think is possible. So this is a bit wordy, but we'll get through it. The definition of passive house, so we consider this a Platonic definition, a theoretical definition. The real world can intervene, but a passive house is a building for which thermal comfort can be achieved solely by post-heating or post-cooling of the fresh air mass, which is required to achieve sufficient indoor air quality conditions without the need for additional recirculation of air. It's quite a mouthful. But what I want to point out here, it's focused on thermal comfort first, per this international standard of thermal comfort that can be achieved by only heating or cooling through the fresh air mass, so the ventilation system that's providing the fresh air to the building. That's only enough air in the ventilation that's coming in that's required to maintain healthy indoor air quality. So we don't want to overventilate. We don't want to underventilate, but we don't want to overventilate. And we're not going to recirculate that air. This is 100% supply, 100% exhaust. And so it's a very low rate of ventilation once you get through the methodology that is actually required, which means you only have the capacity to deliver a very low amount of heating or cooling energy. So this is like the physics underpinning theory of it. We don't actually typically supply either the cooling or the heating through the ventilation system just because of the construction realities and the physical realities, but this is the idea. Shoot for a condition where on a cold winter night where the power's gone out and you can stay warm with a handful of candles, or it's the equivalent of a hairdryer. It's another way it's doing it. And what it really switches in one's mind is that efficiency is driving greater comfort and health, and greater comfort and health can drive efficiency. So it's taking these two seemingly contradictory aspects where we have to sacrifice our health or our comfort to efficiency and aligning them so they're rowing in the same direction. So you can sit by a window on a cold winter day. There's no heater underneath the window. The heater's back on the other side of the room, and you're comfortable. So we want to decouple power from performance. A key aspect of Passive House is that it's going for a fixed target. It's not about incremental improvement. These are low numbers to hit those physical dynamics that we're just talking about. So we need to get down to a really good number. Typically, in our older buildings, in this case a leaky house, here's the line of equilibrium. We have thermal losses below the line. We need to make it up with gains. We have a little bit of solar, a little bit of internal heat gains, we have a big heating system to make up for it. Modern houses are doing better, cutting it down. A passive house really pushes it down to this physical definition and crushes the heating load, as our friends in Massachusetts say. So this reality then is something that we want to make predictable. Now we can build, this is I should have put, this is another slide from Massachusetts actually, but looking at affordable housing in Philadelphia, where the code buildings have a wide variety of performance outcomes. You can do a very efficient code building, or you can do a very inefficient code building. With LEED, you can do great things with LEED, all kinds of sustainability goals that are very important and admirable, but you can do efficient building, a more efficient building, or a less efficient building. It's not really locking it in the way that we need for predictability. A passive house is lower, and it's in a lower level of variation between the worst and the best. And it allows you that predictability in the outcome through the methodology. Another interesting aspect, which we won't go into a lot here, but you can look at EUI, you can look at the operating carbon emissions of the building through passive house. It's not that it doesn't exist, but the focus is shifting to its compatibility with the all-electric, all-renewable power supply. So we are saying, yes, politics may have a way of making it a very bumpy road, but we're going to an all-electric, all-renewable reality in the not-too-distant future, if we have any sanity. And so how well does our building function aligning with this future? It's not really about the emissions of the production anymore, although we want to minimize the amount of those solar panels that we're building, minimize the number of windmills, minimize the number of dams that we need. It's really the simultaneity of the use, and depending on the use, those simultaneity on a daily level, but on a seasonal level, and reducing short-term storage needs and losses, and then long-term seasonal losses, and minimize those efficiencies. So we won't go into that here, but needless to say, it argues that the heating demand is a critical thing in terms of making the future energy supply be more efficient, and one of the critical things that the building addresses. So what are the ingredients? A little bit more on that, the elements of fundamental performance. Well, it is about the structure first. It's about the envelope, the enclosure. There are 5 principles here. Of course, it's more complicated than this. It's building, but this really is at the heart of it. So we've got, and we'll go through this all in a second, climate-specific levels of insulation. We want the insulation to be thermal bridge-free. We want the air tightness to be complete with high-performance windows and doors and solar protection. All of these things are dealing with the enclosure and making that as robust as it can be. And then we want an amazing ventilation system. The heating and cooling is not part of the principles. It's not driving the performance. We just don't want them to undermine the performance, which we'll get to in a second. So really specific, it's going to typically be more than code requirement for insulation. It could be significantly more. It depends on all the other aspects in terms of how you're optimizing the building, in terms of form factor, in terms of other specifications, how good your windows are, how good the heat recovery is. It's all interdependent on the ultimate specification that's required. But let's say, we want to dress for winter in the winter, not be like my daughters who go out in a hoodie in the winter, right? Like many of our kids. And we want to wear a parka and a hat and gloves and a scarf. and know that we're dressed for the weather. We want our buildings not to be like the kids in hoodies, or adults in hoodies for that matter, but dressing for the weather. Like climate-specific rated sleeping bag, perhaps. Again, minimizing that heat load requirement. Thermal bridge-free construction is one of the fascinating things. So we don't want to undermine the insulation. So studs repeating and metal studs with insulation in them can be horrible thermal bridges. But where it gets more interesting is at those connections, right? Between the wall and the floor, the wall and the roof, where structure comes through. And so here's an example. Again, not rocket science here. I mean, there is some math going on in the programs and whatnot, but you have, where's my pointer? You have some insulation coming here, and underneath this floor and wall, they have a piece of masonry supporting it structurally, but its thermal properties are bad. It's creating a thermal bridge. It's not acceptable. We don't need to go into all the details of it, but to say that by simply changing out one material for another, in this case, aerated autoclave concrete block along there, we can change the thermal dynamics of that corner and eliminate that thermal bridge. Adding up all these thermal bridges and putting them into the energy model, they can have a gigantic effect on the overall building energy use. And is one of the reasons why mechanical engineers will want to oversize the building's mechanical systems. They can also undermine comfort and health. That if we have thermal bridges and the interior surface temperatures aren't high enough and we have relatively high indoor humidity, we can have condensation and mold and things that drive sickness. We have energy loss, very typical construction with the concrete balcony going through the enclosure. I was thinking when Bill showed the pictures of Miami, all those buildings with the balconies and everything, they're all just thermal bridges. Those are just huge radiators to the world. So problems in a bunch of different directions here. But we can, again, address some things rather simply. So here is a window. It's a passive house window, perhaps, but it's sitting just straight on the framing here, and this wood is creating a thermal bridge. And here we have a double stud construction at the window. We have the insulation in line with the insulation of the window, and it reduces, it improves the thermal performance to make sure that it's providing optimal conditions. With the insulation and thermal bridge free, the air tightness is super important. And it's one thing that people maybe are a little nervous about initially, because the idea of being trapped in an airtight environment. You're not trapped. You can open the windows and doors. If it's a nice day, let the air blow through. Natural ventilation is a core aspect of passive house design. The problem is you just can't depend on it, right? What if your building is in a polluted environment? What if there's wildfire smoke? What if you're allergic to all the pollen in the air that's outside blowing around? You don't really want all those outdoor pollutants inside. So in terms of health and having high quality indoor air tightness is kind of the prerequisite. We want to get control of that air. It's reducing drafts, so it's more comfortable and more energy efficient, not reducing the heat loss. Reduces moisture damages, which is a whole other talk about how really air tightness is more important than the vapor control, although vapor control is also important. The damages really come from air tightness. And so we have control of that interior air. Like a windbreaker over a fleece sweater, it's enhancing the power of the insulation as well. Think of the windows and doors are climate specific. they're extensions of the insulation layer, of the air tightness layer. So typically in this environment, we're going to have triple pane windows. We're going to have truly thermally broken frames. It could be of almost any material and construction type, depending on the project and the specifications. We're not using them. We are using their solar, their passive solar collecting ability to help those, to help provide passive heat gains, but we don't want to over-rely on them. We don't want to overheat the building unnecessarily. And so part of that is to be really cognizant of what we're doing with the orientation of the windows, but also have solar protection. So use all your space comfortably. You can go right up to the windows. Yeah. So big driver here. So basically, the typical windows, you're going to have the surface of the windows going to be too cold, right? And you're going to have convective currents. You're going to feel the radiation loss off of your body. We need to put mechanical systems at the perimeter. With a passive house, we want to bring up that surface of the window to close enough to the indoor air temperature so that you're not feeling that thermal discomfort that has to be overcome with mechanical systems at the perimeter. Consequently, we can pull the mechanical systems back to the interior. Here's the shading. So shading, we want to consider and include it. You know, again, going pre-World War II here, modern architecture, you know, back in the day had lots of built-in shading. We can think of great Corbeau projects. They were, you know, terrible thermal bridges perhaps, and perhaps the upfront carbon wasn't so good. But he had the shading in, and we really need to bring it back in a big way to have the focus on that. Thinking about the landscape, architectural elements, the window pockets. You can have occupant-controlled shading, of course, but the less occupant-driven performance, the better, obviously. So really, again, investing in the architecture. All right, so those 4 things give us the basic envelope enclosure performance, the basic elements of that, and then the ventilation. So the ventilation is being supplied 24/7 to all the served spaces. Fresh air is coming in, it's filtered fresh air. It's going into the bedrooms, the living rooms, the classrooms, the offices, the conference halls, and being exhausted from the served spaces, the bathrooms, the kitchens, the utility rooms, hallways. It's balanced, and it's relatively low flow for what you would imagine, again, because we have control over that air now with the air tightness. So it requires a very small amount of energy to maintain a high level of quality. And with that air, we're going to recover a ton of the heat that's coming through. Yeah, fewer allergies, less asthma, more healthy. And what's happening in terms of operation is just a fan, like our bath fan or kitchen fan. It needs to be a very efficient fan, but the heat recovery is happening as the extract air is going through a heat exchange core, passing by the supply air. And we can now recover over 90% of the heat. So even in the cold of winter, you have fresh air coming into the room within a few degrees of the interior. You're thermally comfortable. You don't need to, again, compensate with heating or cooling for it. And the ventilation efficiency, once you dive into it, is hugely important in terms of the overall energy balance of the building. So those are the 5 basic elements, are salt, fat, heat, and acid of building. Then we've got control. Then we're right-sizing the heating and cooling. We still need them. Passive houses do have heating systems. They just should be really small heating systems. So we're looking at typically a 75% reduction. That house that I got when I started doing passive house was a a retrofit of a 5-story townhouse in Brooklyn Heights. And it was like 5,500 square foot building. It was a big house. And all the neighbors, similar houses, had 12 to 15 tons of air conditioning on the roof of the building. And it was in a historic district, and there was nothing landmarks could do about it because it was the mechanical system. We calculated the heating and cooling demand, and we calculated that we needed 1.5 tons for our building, which is a really scary thing when your client's spending a couple $1 million renovating their new home, and you're saying, well, the equivalent of a window unit for a typical living room would be sufficient for that. And it is the methodology, you know, and the calculations that give you the confidence of the predictability to actually do it. Now, there's variation, right? And that was at the optimistic end. So we did install 3 tons. But it's between 1.5 and 3 tons, right? It's really still a pretty flat line in terms of the use, which very happy to report that the house went through the summer, you know, the heat and the winter cold fine. So we want to downsize those systems. Typically, they're all electric. We can have smart controls of renewables too, but we want them to come after we've made a great building. So they should enhance high performance, not compensate for poor performance. That's really the key thing. Start with something great, make it better. Don't do something poor and say it's good enough because we've put stuff on it. So it's all about this optimization. Is you're using energy as a design tool. You're using energy with all the other programmatic aspects to optimize the architecture and lower that demand. It has global application around the world. It's basic, just physics, fundamental principles. There are all kinds of applications. So tools, just super briefly here, there's education, and I would be remiss, we actually provide certified passive house designer training, and we have a course starting this Thursday, coincidentally, which is online. It's on demand. It's a mix of on demand and live online hybrid. It's very flexible. By Christmas, you could be a certified passive house designer. And there are a bunch of different incentives available. So I encourage you to go on passivehousenetwork.org and check it out. I'll leave it there for my plug. There's also tradesperson in the PHI universe. There's also certified passive house consultants and builders, a whole world of certified people working on the projects. There's also components, which can be hugely helpful, especially the critical ones. We talked about the windows. We talked about the ventilation system being really incredibly important. These have been tested, and the specifications are in the models, and it just helps, again, with the predictability. And then building certification. I'm not going to go into the building on the right, but I will note it's by Grimshaw Architects in Australia. It does not look like a passive house, I'll tell you. It's a huge building. It's worth looking up. But there are different certification levels and different types with renewable and electrical balance included. And there's Enerfit. I'm very happy to include this slide. I think we may hear more about it this afternoon from Bruce, the Hotel Marcel, which is a wonderful example of Enerfit and this optimal integration that we're talking about. So just a quick run through some examples just to show that sort of anything is possible. I mean, we're still dealing with the physical reality. Like say, you know, architects don't have too much of a problem, at least once they're out of school, dealing with gravity. We have to deal with gravity as architects, but we need to treat energy in the same way and see how our designs are reacting. So big, tall buildings of various types and around the world, affordable housing. Sendero Verde's got a fair amount of press in East Harlem. This development won the Sterling Prize, which was super exciting in the UK. So really like bringing design to it. We'll see if this one on the left ever gets built. It's been through like 100 iterations that really have nothing to do with Passive House. Most of the time, quick note, when people, well, I should say, most of the time when I'm talking to somebody and they're kind of venting, their Passive House vent comes to me. It's like, we're having this problem, that problem, blah, blah, blah. And we start to say, okay, well, let's unpack this. What are we really talking about? What's happening with this? And more times than not, it's construction, it's design, it's clients, it's all the problems that we have in making a building, which is really hard. It's not necessarily the Passive House aspects that are driving the problems, usually not. Anyway, long story to say, Herzog de Meuron is doing this big museum in Vancouver. The embodied carbon's not looking great at face value, but who knows what they're doing. They're a smart firm. Belgian embassy in Kinshasa, Congo. Administrative building in Brussels, just all sort of shapes and sizes. The university in Bar Harbor, Maine, College of the Atlantic, which is beautiful. I'm just about done. University of Cambridge, indoor leisure facility. And this is that townhouse in Brooklyn Heights. You wouldn't know it. In homes of all kind of more traditional, more vernacular, more modern, anything is possible. So really the thing is building a culture of quality, the intention, focusing on those drivers, focusing on this idea of comfort, hygiene, and efficiency. Anyone can do it. So I hope you do too. Thank you.
Thank you, everyone, especially to Adina and Katie and the Committee of the Environment. I'm very honored to be here. The name of my talk is Embracing Building Science to Design Low Carbon Environments. I use the word environments because much of our work entails more than the building, the landscaping, stormwater treatment or development, and transportation, cars. And it has been a goal of mine to learn more about building science to help me design better buildings. This is just an image of, in the middle of a LEED platinum building that I designed in 2008. It was a turning point in my career because I wanted to see if I could design a building to meet that standard. And I actually was my own property that I developed. But when after I accomplished that, I learned about the Passive House standard, and I was so humbled by how much I needed to learn. And since then, I have been doing Passive House projects, and I'm going to show you 5 different buildings, different projects. They're each different types of projects. A single family retrofit, a very old 1815 building, a new house, a mixed-use historic landmark building, and a new mixed-use building. And I'm showing this to you because I hope this will inspire you to see how we can make a big difference and how the Passive House standard can apply to any building. And of course, these are all the logos I've been collecting, of the different standards that we've been following to get us to this higher level of sustainability. A little background, I'm sorry, before I go this way. I had a practice for 36 years in Hastings on Hudson. I've always had a commitment to have environmentally sensitive buildings since I studied architecture during an oil crisis. And then that seemed to completely go by the wayside during the 80s. I learned building science along the way, taking many courses. In 2012, I took the FIAS course in New York City. Katrine Klingberg was my mentor. And she said, you know, the architects, you should set an example. If you build, set an example with your own home, which she did actually. So I decided as soon as I had the opportunity, I would do that. And I downscaled my big house a few years ago to a new house. Well, it's actually a retrofit. And I've been using my house as a learning tool, giving tours, giving talks about it at the local library. I've also been doing passive house workshops in my office, and a variety of things that will really help promote building in a more conscious of a more reduction of a more energy efficient way. This is the 5 concepts of passive house. I'm a little glad that Ken Levenson went through this with you. When I give a tour of our house, which was finished in 2022, I start with this diagram. I also have and actually I've been inviting the public to my house. I've had architects and neighbors, local politicians, and I will put an ad out on Monday morning before the tour on Saturday, and within 2 hours it gets completely booked. There's so much interest in this. There's no reason to feel that there isn't. But I have always believed we need a grassroots way of promoting sustainability as architects, which means getting out of our silos, collaborating with the local, with your community, with your local government, and getting involved in lots of different organizations. This is, I give the, my audience when they come into my house a little, for a half an hour I teach them about passive house. I also show them that video about passive house in 90 seconds, which everyone adores. And I think they can understand most of these concepts. But the thermal bridge free, I describe it as if you're going outdoors in the wintertime, what would you use if it's like, 10 degrees? You would wear a down jacket. So I compare a passive house to a down jacket because we want to have really well-insulated building, continuous insulation as airtight as we can. So we would have a down jacket with a hood on, and everything's wrapped very tightly around your face and your hands. And thermal bridge occurs when you have a gap in your insulation. And try to make it as clear and simple as can be so they understand. So if you have a stud wall house, which most people have, each stud is a thermal bridge unless you have some kind of continuous insulation. And it's almost like going outside and with a denim jacket that has little like almost holes in it. So this is my own house that I started out with. A little house that was built in 1905, and I actually looked for a house that I could change and make into zero energy passive house. And I've had, by the way, I've had tremendous support from the U.S. Department of Energy. Again, I've reached out to lots of different sources to learn about building science. They're given me tremendous support and gave me an award, and just recently gave me another one. But what I like about the US DOE, if you look at their website, they have the WHV software on their website that's for free. And I started using that, I think, about 10 years ago. It's the WHV energy modeling. So, they really are been a great support. This is the house originally. I actually chose a house that would be really close to the downtown. My plans for doing a passive house started before the pandemic, and not knowing people would be working remotely, so I wanted to be close to my office. And if I lived here, I wouldn't have to rely on my car. I thought about the big picture, not just the building, and I wanted to reduce my dependence on the car. And I also, so it's very close. It's about a 5-minute walk to the downtown. And so also about a 7-minute walk to the train station. This house was really at the end of its life expectancy. I mean, really in shambles. The family had owned it for 47 years, and they tried to hold on to it because it was precious to them, but the taxes were very high and they couldn't maintain it. They actually had 4 children in this house, and it was only 954 square feet. I love to tell people this because carbon footprint relates so much to also how much space we use, how big our houses are, how many cars we have. So why do people want such big homes? When, you know, these 4 kids grew up in this teeny weeny house, and I'm sure they're not like emotionally damaged because of it. I start out by showing them, I'm going to show a few plans. This is the original house on the, I guess the plan on the left is just the original house in gray, and the yellow around it is the new build out and thermal envelope. So we wrap that entire house with a new structure, a new thermal envelope. And on the right is the fully developed plan with solar panels on the southeast plane of the roof. And we have a rain garden in the back that helps to take care of stormwater for the site. We added, we went from 954 square feet to 1,700 square feet. I show floor plans to my audience, and they're mostly not architects, because I want them to see that you can have a really small house, and it can really serve so many needs. If you look at it in a way that you're saying if you conserve space, you conserve energy. So conserving on floor area, you can do that by having having a very open space. You only have, in this house, there's only 2 people living there. But we have 1 living space, and it's multifunctional, like it was, before World War II. And most people had 1 living room, 1 dining area, 1 kitchen. And all these spaces are located on the southern side of the house. Orientation is critical because the primary source of heat is the sun coming through south-facing glass. So the front of the house has a porch with glass, and all the primary spaces that we live in, and all the bedrooms have south-facing windows. On the north side is where we located bathrooms and closets, side entrance. And actually, we were able to get sliding doors facing northeast because our energy model, when I was designing, and I use energy modeling to design, told me that I could still have that amount of glass, which gave us a nice view of the backyard. We have 3 rooms upstairs. I always like people to think of them as flex space. Why? There is such a demand now, especially for home offices. They want 1 bedroom per child. They want 2 home offices, usually his and hers. So houses are getting bigger. Why not have them multifunctional? So, the large bedroom is the primary bedroom. Middle one is exercise, secondary bedroom. One in front is a home office and studio. So we combine uses, especially when you consider how many people are in each room at any given time. There's only 2 people in the house. So, this is a nice learning experience for people because they seem to think to follow the American dream, you need 4 bedrooms. The extra one for the guests is hardly ever used. And then you have now his and her offices, and the houses somehow are getting bigger sometimes. And then, of course, all the bathrooms are on the closets on the north side. This bathroom is a combination. Actually, you know, it's just conservation of energy and carbon, I think, has been a driving goal in our designs. So instead of having 2 bathrooms with 2 toilets, we only have 1, and they're combined so that when a guest comes, you can lock the door and it's shared. And it becomes now a hall bath for someone visiting. But it's designed with intention only for what is necessary for the residents. And these are our, just to show that the design showed we have a trellis and a porch, and the trellis inside, we found ways for solar shading of these windows facing south. North side, little windows, of course. And these are just sections to show the heavy thermal envelope. We actually, to conserve on sending waste to the landfill, we saved as much as the old house as we could. We saved 2 walls, we saved the foundation because we didn't want to add concrete if we didn't have to. This is our, just the detail of the thermal envelope. We have double stud wall. I did this during the pandemic, and I wanted to keep it simple as possible. We had 2 different contractors. This is the first tried to train their people. It wasn't so easy. We had a second one, knew more about passive house, but the stud wall kept it simple so that any carpenter could build it. And then we filled this cavity between, the red line is the interior air barrier, and the exterior, and the blue line is the exterior membrane, weather-resistant membrane. And between those 2 membranes, we filled it with dense packed cellulose, very much like a down jacket, where you've got 2 membranes. One is for water resistance on the outside, and the interior is an airtight membrane. You fill it with insulation. This is the energy model we used. This is before the drawings were finished in the design phase. I start out by using a WHV model to see if we're going to hit these targets. And that helps to determine where the glass is, how big it is, and it's all a matter of energy balance. So we had some glass facing northeast, but we have most of the glass facing south. And you see on the model, we also have our solar shading to help reduce the cooling load in the summer. This is the house when it was stripped. We decided that we would save the framing on 2 sides of the house. We added 8 feet to the house, so we made it a little bigger than it was. This is showing the double stud wall. The old house is in the back. The new house is swallowing up the old house to create the new thermal envelope. We took out the sheathing. We used cross bracing so that we could have continuous insulation between the 2 studs. Old studs are in the front, newer are behind. This is when you see, you know, all the studs, all this framing to create the envelope. This is our exterior envelope, weather-resistant, our exterior membrane, the weather-resistant membrane. It's all taped and sealed. This is our interior membrane. They call it smart membrane because this membrane has been designed to allow vapor permeability, and we want to make sure if there's any kind of condensation on the wall that can be drying to the inside. I also had a hygrothermic analysis done by THEIS. They offer that service for very, very minimal cost, and they will do a time-lapse simulation of weather hitting your thermal envelope to see if the dew point is ever hit during the year of weather in your climate. I have done this for a couple of projects when clients are worried about mold. You see all those horizontal strips of wood. This is to create our service cavity for our wiring. Second floor, see the interior envelope, the interior membrane. And then we did our blower door test before we finalized the building. This is to make sure we're going to meet our targets. We sailed through, we had 0.02 CFM per square foot for its test, but we ended up at the end 0.05, but still met the passive house targets. This is just these tubes falling down. These are coming down from the ERV, the energy recovery ventilation unit. We have that up in the closet of the primary bedroom, and the tubes come down so they provide supply into most of the habitable rooms, and then returns from the kitchen and the baths. This is our unit, which we had mounted so that we could reach it. It's on the wall of the walk-in closet in the bedroom. And we're so aware of this unit, and we love to show people how how we use it, how we take the filters out. And I really wanted to take the mystery out of passive house. And yeah, it's a simple fan, really. And but I'm aware that we get about 1 air exchange per hour. So like during the pandemic, when people would come, we'd leave the house for an hour to feel comfortable getting back inside. And this is all finished. We took out all the entire lawn that was in the front and back of the house, put in a native garden. And as you can see, what I think is really interesting about this image is you can see the amount of solar shading going on. We have the porch. This is probably in early August. We have the shading from the front porch, shading the glass next to the front door. We have the shading of that door almost completely by that trellis up there. Oh, actually, this is about half at this time of day. And then we have the shading. I introduced this angle deliberately because I knew I would get full shading of that glass, that tall piece of glass. That faces due south. Most of the year we have deep overhangs, and then we have a trellis on the side. And there's just a few more photos of the house. I designed this trellis, very simply made, very simple. There's a bracket that I have a sample of this metal bracket that I've given to different contractors to match. And this has all been designed using solar shading calculations, very simple calculator that you can find in various places on the internet or from 475, I think. And by angling these, the wood like that, it completely blocks out the sun. And the depth of the trellis is based on this solar shading analysis. North facade, hardly any windows, very small. They're in the bathrooms and in the stairway. You can see the old foundation of the house. Don't want to use new concrete if I don't have to. And here is the big overhang. And inside we have this delightful space. This is the entry, and we made it it's an entry, but it's also for my piano and just a really inviting space. This is our living area, which sometimes becomes a playroom for the grandchildren. Open kitchen, since it's not very big. Walls are solid on that side. That's northwest. Primary bedroom. This is a night. What's fun about this picture is I wanted this to have this similar scale as all the other houses on the street, and each house is a different design, and so that was also important to me. So it's interesting how you can design a passive house and then have it just fit really nicely in that neighborhood. We're the only all-electric house though on the street. We took out the oil tank. There's not a single all-electric here, but I know a lot of our neighbors, almost all of them, have been in the house and they're really intrigued about some of these ideas. Now, this is a second project I wanted to show you, and that's because this was, it was completed in 2018. This is my first passive house project. This house was built in 1815, and you have a lot of, I think there is a general opinion that you can't make an old house that old meet passive house standard. Well, in order to do so, we actually gutted the house, so there was a lot of it was a deep energy retrofit, and we added these two additions. Our client was from Ireland. He knew the PHI standard, and he was a contractor. And this is just showing some of the construction photos. This is such a great image because it was my client's idea, who studied passive house, to hang the new structure. The new structure is those joists running that way. And that big beam is holding up the old stone wall. And we're hanging the joist. And that's because we ended up having insulation between the joists, wrapping underneath that beam, and then back up into the wall of the house. And that way we avoided a thermal bridge. And we had client and everyone, and head framer and myself were all knowledgeable, or we became knowledgeable, and found out a way to overcome these challenges. And this is the stud wall. I think we wouldn't use metal in the future, but he was a New York City contractor, and I guess he had that material. We used dense packed cellulose for the fill inside the walls, and then mineral wool, continuous mineral wool on the outside of the studs. This is a sketch on the right by the head framer, and this is my drawing on the left. And I always amazed at the amount of collaboration that occurs in order to reach these standards, especially to overcome the challenges of thermal bridging. We have these decorative brackets that we added to the roof to mimic the brackets on the original old house built in 1850, you know. And then he did this sketch because he's showing layering the brackets with wood fiber rigid insulation to reduce the thermal bridging that occurred because of this detail. And those are the brackets there you see under the overhang. This is some of the views of the interior. We have, this is one passive house I have two where we've had clients who really want a fireplace, but this is a fireplace made in Europe that is airtight once it's closed. And the owner is taking responsibility to making sure that it doesn't open for long, so that we can control the air and make sure there isn't any kind of negative repercussions from using it. But he rarely uses his, doesn't need any heat. This is middle of the passive house standards. This is another project. This is a new house, and this is a LEED Platinum passive house zero energy project. This is a house that started with an old house, and we kept most of the structure that was there, the foundation and the framing, and we built onto it. It was in terrible condition. We had some fun with some curves because, of course, the garage is outside the thermal envelope. We added porches because most of the orientation of the house is facing southeast and southwest. This is our site plan to show how we developed the house so that we had one facade facing southeast for solar panels, wraparound porch for shading, reducing our cooling loads in the front of the house. And that funny oval there is a rain garden, which took in all the runoff from the site and the roofs. Floor plans just showing, we angled the garage to keep it away from the trees along the property lines right up next to Teatown Lake Preserve to make sure we didn't disturb the drip line and the roots of those trees. We do have, this is a house, we have a his and hers office. It's a bigger house than mine, but it's has interior conditioned space of 3,500 square feet. And these are the elevations. Okay, on the north side, we've located bathrooms and minimized the amount of glass on the north side, and then have a tremendous amount of glass on this is the southeast side, that's southwest. And on the southwest, we took care to have solar shading with trellises, and then the porch to reduce our cooling loads. The section, that structure on the right is actually existing. We kept that part of the house and kept the foundation. We have two membranes, exterior, interior, and filled it with dense pack cellulose. We actually put in the crawl space recycled EPS rigid insulation to complete the thermal envelope below the floor. And this is just a diagram showing general concepts following the 5 main elements of a passive house design. 1, thermal bridge elimination. 2, continuous air barrier. 3, thermal envelope. 4, high performance triple pane glass windows. 5, energy recovery ventilation system, which we actually moved up to the attic, and we had the outlets going through the gable end walls. And the certification, Zero Energy, Indoor Air Plus, Energy Star Passive House. It's actually FIAS 2018 plus certification, and LEED Platinum. Now, our client was a mechanical engineer, and he was on the sustainability committee in his village in Ossining, and he wanted to set an example. And he really asked me if we could meet all these targets, and I was so thrilled to have a client like that. But we have a lot of clients that don't care about the certification. But we decided in our practice we're going to do it anyway. We're going to present the options, and we're going to, if they're coming to me with a project, then I'm going to show them how we can meet these high standards. But a lot of it starts with the energy model. I will do an energy model of a design very early on in the design phase. And then once we get that model set up, we can look at different options to show them how you can, if you don't do certain things, we won't hit the target. And this makes them feel like they're part of the process and helps to spread the knowledge. So these are some images during construction. This is a Larson Truss. We salvaged as much as we could of the old structure, and we used a lot of the lumber from the old house to create scrap lumber to create Larson trusses. They're like homemade trusses to build out the exterior wall and create the cavity for the dense pack cellulose. This is our blower door test done during construction and then after construction. This is when we're finished. Above you see the trellis detail, the same bracket in my house. And then you see how much shading of the windows due to where the window is set in the opening, also roof overhang, the trellis, and the front porch. And this on the right is an image of the landscaping. We hired a landscape designer who only does native gardens. We completely reinvented that property. This is the porch. This is a thermally modified ash decking because we know, we think about in our office about, what not just will get our points for LEED certification, but also just to be responsible for what we use, because this is not using ipe and those materials that come from tropical forest. This is the interior again. The owner's mechanical engineer, and he got the notice from FIAS that said there could be, you're in mortal danger if you use a fireplace in a passive house. This is a very special fireplace. It's sealed. It has tremendous air tightness, and you have to open the glass to put the wood in it, and he's going to take responsibility for that. This is my fourth project to show you. This is a mixed-use historic landmark retrofit in Yonkers. I figured I probably like a lot of architects in Westchester, we are working mostly on old buildings. This was built in 1880, and we've been restoring this building. We had to meet very high standards for the Historic Landmark Commission in Yonkers. And in this case, we're meeting the PHI standard. This is the way that building used to look. These are our drawings, and I just brought this so that you could see when we did we look at the thermal envelope. In this case, we have a solid 8-inch brick wall. We are creating a cavity on the inside, and we're filling that. Well, first of all, we're using wood fiber rigid insulation, which is taped and sealed for our weather-resistant barrier, and it's also used for continuous insulation. And then between that and the red line, which is our interior membrane, is our cavity that we filled with dense packed cellulose. And then we have our service cavity. We always make sure there's a space for wires and pipes so we don't penetrate that thermal envelope. Just like trying to save that down jacket and making sure you don't put holes in it, which is going to really compromise the effectiveness of the thermal, of your energy efficiency. This is the same building in the WHV model. I added the buildings around it, which you see in these skeleton shapes, are actually buildings that are providing, putting shade on the building, and it's very important to have that part of the model. All those arrows coming out is heat. It's just showing that these are areas where you're getting heat loss from the interior space. And I have found this a great tool to tell us when we're in the design phase if we're going to meet our targets. So all those check marks show that. Comes to heating, cooling, demand, heating, cooling loads. We are doing very well. Site energy, not so well, because this does not take into account any solar panels. And yet we're still meeting the passive house standard. My fifth project is this one. This is a mixed-use project in Hastings that I'm working on right now. We just went to our first planning board meeting. Our target is to meet FIAS, is to get passive house certification through FIAS. It's very challenging because here on the right we have this beautiful old building, solid brick wall, 12-inch to 8-inch thick brick wall. So we're going to create our thermal envelope on the inside. A different condition for the building on the left. This is a new building. We're going to have a veneer, stone veneer, and then on the sides panel veneer, and we're going to create our thermal envelope in a different way. So we have a lot to consider. These are just some other images of our 3D model. New building on the left, old building on the left, new on the right, and just different images of the model. We have pictures of the building when it was built in 1918, and they have these wonderful awnings that they had on the windows, and we're trying to see if we can replicate that to do something that really ties in with the historic nature of this special building, and we have to consider so many things when we put this in our energy model, because this whole facade faces south, great for heat, but not for cooling. And then we have a whole facade facing west, and we might consider even having, this is our west facade. We will need a variance for that, but I'm hoping I can get that variance and add porches to this facade, because I feel that when you have west-facing glass, porches really help to reduce the cooling load, is much more effective than anything else because of how deep the sun is, how low the rays of the sun are coming from the west in the summer. This is the energy model, so it's a big difference between the rendering of the design, because when you do an energy model, you have to look at the thermal envelope for the space that will be meet the passive house standards. So we took out the commercial space. So this whole piece here has been taken out because we don't know what occupancy it's going to have. And we took out the garage, which is outside the thermal envelope. So we're taking a look at the thermal envelope that goes around the residential portion. There's going to be 15 units here. And we are just in the early phase. I was hoping to get the model finished by today, but this is simply the beginning to help us identify the old building, new building, the areas of the building that will be in the thermal, but we will model that's in the thermal envelope. And when you do this model, you have to make sure all the lines connect, otherwise it doesn't even register. So it makes you think about having a completely continuous thermal envelope all around the building. Next step with this is this gets put into the WHV model, and then we have now a prototype for each one of these 5 buildings. We have a prototype for a retrofit, single family, new house single family, mixed use building. And in the mixed use category, we have about 3 different prototypes, depending on the construction we want to use. And once you set up all your assemblies in the WHV model, you can use the same prototype to take your model, you put it in there, and you pick your, I picked the prototype that I think is going to go with this. I'm going to use a different one that more relates to those historic buildings for the old piece of the building, and then one for new construction that I developed in the WHV model for this piece of the building. This building's about 27,000 square feet. And I'm going to end with that because I wanted to show you how we're applying passive house principles for both small and large projects. I mean, for Westchester, large is usually not more than 3 stories. I'm going to end with this image. This has become a reference book for our firm and also for friends and family, because Henry Gifford, you know Henry? He put together this beautiful book. It came out in 2017, and it's amazing. It's a beautiful book. There's like lots of pictures, and he really goes through the fundamentals of building science. And in fact, the name, the subtitle of the book is Better Buildings by Understanding Basic Building Science. And I just want to leave you with that thought, because I really feel that that's what we need to all do, is to embrace building science, to build and design better buildings. Thank you.
All right. Thank you so much. This has been a journey. I don't know if all of you have felt the same, but we went through so many topics and certifications and different ways of measuring and quantifying data and carbon, and it kind of gets into this like wormhole of what to do and how to do it. My first question, until we get start sorting out the questions from the audience, would be, how do you navigate through all of this? How do you make sure that during the beginning of your design intent, you're able to do this throughout the bidding process, to the procurement, to the actual building it? How are you able to do that? So I guess in your own practice and in your own experience, tell us about.
Yes, this one's for me. Well, I collaborate a lot. I think I call Ken. No, or, well, something close to that, because there's Nick Shaw. He's probably hears from me every few months. 475, his company, has been incredibly generous with assisting architects. They even have drawings for free of different thermal envelopes on their website. And I collaborate. I am very humble about things I don't know, and I'm always coming up with a different situation, especially with old buildings. So many different ways to do this, really. So I problem solve, and I encourage my team, my office, to do the same. So we have like group Zoom meetings to how do we navigate it. Well, we try to really put together the drawings and specs that has everything in it. And it's been, you have to be disciplined to even get passive house certification, because they require you get pre-certification before you build it. So usually it's all spelled out to a lot of detail, thermal bridging is resolved. But then on the construction site, we do come across problems, and then we make sure. Most of the successful projects, we have people who did some training with passive house. There's a passive house training program, and there's usually only one or two of those guys on the site, and they help guide the others. So I guess I hope it's always, there's always something that might not have been worked out the way it should have been, but that's the process we've been following.
Yeah, I would add to that. I think it is one of the things to move through is to embrace it. The passive house, I see it as sort of this gift of focus on the pathway through it, and on an early project to go for certification, because certification kind of forces your hand to be rigorous in moving through it. And I see the certification process as a bit of like the apprenticeship, that you may get certified and learn the basic principles and everything, but it's like coming out of architecture school. It's like, are you really an expert architect coming out of architecture school? And so going through that process, working with the certifiers who have just a ton of experience and expertise to be able to share with you, and take it step by step through. And I think, as Christina is saying, to the extent that everyone on the team has some training, it could be different levels of training or awareness, having the common goal and understanding it. We've seen in the projects, like a lot of my projects back in the day were in Brooklyn, retrofits, townhouse retrofits, all kinds of construction crews from all over the world, right? And just having a little bit of training that's focused on specific things, they can get a sense of how their job affects the ultimate performance of the building, and they actually take ownership of it. And it's not an elixir by any means, but we have seen repeatedly where the builders at all levels, along with the engineers and the architects, kind of embrace this collaborative effort that Christina's speaking to deliver really high quality building, and feeling like they had a meaningful role in it, and are really proud of the product that they've delivered. And I think just, and then to bring, it's continuous, so you're bringing in more and more information, but to keep it simple to begin with.
Yeah, and I would add here, because I know, Christina, you did mention about having, previously in our calls, about having a 1-point person or something that's from the design that kind of helps the transition into the actual construction. So it helps facilitate making sure that things don't get swapped out during bidding or stuff like that. But there is a few things I want to bring Bill a part of this conversation, where maybe passive house maybe just focused on just maybe operating, but it's not always the case, as we see that a lot of passive house designers not only just focus on the solely principles of passive house, but they take this to a broader aspect of trying to figure out how they can include embodied carbon as well as operating carbon. So that's something that also was included.
Well, first of all, although I have a master's in architecture, I am not a working architect, so I can't speak to the burden that all of you have. And it's easy for me to, I have this natural ability to point out every solar panel that's got a leaf hanging over it. But the thing that's, that sort of got me into this was just coming to the realization that there's a big difference between the labels green and sustainable in real life. And, you know, coming out of architecture school, it's labels. And, you know, to be fair to all of you who have this burden, we just didn't know about a lot of this stuff. Even 10, 15 years ago, embodied carbon, what was that? Nobody talked about it. And so, you know, from my perspective, the key to all of this is common sense. And whatever you're doing, because I mean, not everybody, and probably a very small percentage of architects are going to be going for the kind of certifications that two of you do, especially Passive House or some of these other ones. Energy modeling clearly is fairly standard now. But to incorporate this new thing, which is the embodied carbon, at this point, we lack sufficient tools. But however, it doesn't take much sense to, if you sit back and think about it, that there's so much that we can do just by keeping that in mind.
I just want to follow up on what Bill said, because it is really very much in the hands of the architect to help to decide on things like carbon, embodied carbon. I always like to pull down the list of insulation materials that are out there and show them a client what the embodied carbon is for each one, because there's usually a contractor out there will use a spray foam, and they show them the big difference between that and dense packed cellulose. And I shame them into putting that option to the side. But it's not easy. You need somebody who is in charge, I think, and thinking about all these things all the way through, which is one reason why I left a big firm to have a smaller firm, because I really want that, the mind behind the design to follow it through. So all the way along, we're looking at the same, hitting that same target and not making those substitutions because of cost. Cost is always a factor, of course, but not making the wrong substitutions to, you know, lower the standard.
And in terms of like now we're looking at potentially this is going to be a regulation for embodied carbon in the state. Like how is this going to be morphing the way that you practice in terms of the tools that are available, and especially the concerns that Bill brought up, maybe like getting your EPDs isn't as reliable. How do you stick true to your design intent and making sure that the carbon, your goals of carbon reduction actually stay throughout? Just curious about what your thoughts are on this.
Right. Well, first let me ask the audience something, because in the end, all of this requires some form of modeling. So energy modeling is where the two of you really sit, and it's the key to everything. So how many of you, if any of you, do whole life cycle modeling? So one, okay. So two. Educationally. Oh, education, okay. So therein lies the big problem. Because it's fascinating. You know, I did the COTE thing in California exactly 6 months ago, and out there I was shocked because like we had about 200 people, and I would say almost everybody there was involved. Most of them were with medium to large firms. We're doing that because the state is requiring it. And it's going to happen here. So the reason that New York State Executive Order 22 and New York State Executive Order 23 is requiring for certain materials the submission of EPDs, concrete being one of them, is to develop the standard, develop the model, and so because in order to create legislation, then you have to have a standard. You need to benchmark. And so what's happening now in New York State, and it's going to impact all of you, well, first it's going to start with larger buildings, larger being 5,000 square feet in New York State, is that, in fact, also in New York City, they're already on the way to thinking about starting how to incorporate some standard for embodied carbon per square foot of buildings. And so probably 3 or 4 years from now, as this data is collected, those standards are going to start to hit. And then what all of them require, which I have a problem with, and I try to express, is that every one of these buy clean laws, or buy clean programs, I should call them, all starts with, the first thing you have to do is the whole life carbon analysis, which from my point of view, since most of it is speculation, is literally spinning wheels. When I said this in California, a lot of people were unhappy with my saying that, because what they're doing is based upon it. And that's what's being taught in school now, as a matter of fact. But yes, that's important, but it's speculative, and we have a crisis, and we need to deal with the upfront part first. But what's worse is that we don't have the data. The data is all based upon what's coming out of these databases like building technology, building transparency, and that database, most of the stuff in it is garbage. And in fact, what's interesting is out in California, most of the EPDs for concrete that are now doing it properly, based on the specific lot of cement that they procured to make the mix, and are now properly reporting it, the actual emissions are less than what they were reporting before. So they were inflated. Now, coincidentally, that means that the standards that are being used right now for the Inflation Reduction Act, $4.5 billion of money, are based on the inflated standards. So the bottom line is that the legislation that's going to come into effect is going to be based on inflated standards. So it's meaningless. What the money spent is going to get is what it's been. So so the bottom line is that we really need to use our common sense at this point, which we can do. When you start to look at this stuff, or just being aware of it helps. But it doesn't take much for you to look at the initial carbon up through certainly delivery of your product, even if you can't deal with, well, what is it going to be for the installation of the product?
Yeah, I would just add, I think it's important. There's so many requirements coming on, and there's strategies, and it's exciting, and we can tackle a whole bunch of stuff. It's also kind of overwhelming, and it's like I felt as a professional like paralysis about where to start and what to tackle. But having said that, I do think it's really encouraging to see the movement, like in industry around the upfront carbon, embodied carbon, that there are suppliers and supply chains that are being built to serve this part of the industry, and that people who are cognizant of it. And so there's, the range of insulations, for example, we're very cognizant of. There is any number of things where we have more and more options. So, and they're being put forward. You don't have to, know the secret sauce. It's more and more obvious. And I think DPD development has a lot of issues, and that's part of the process. But it is moving, which is exciting. I think Passive House as well, and the two together really to drive down what will be, what we need for the future.
Yeah.
I think one more comment here, which I discussed with you actually. For those of you who now or will work for mid-sized or larger firms, where you're going to be, going down to, there'll be maybe a couple of year process of taking your design to detailing and then going to a spec writer that's going to go at the bids. Therein lies the key question, which I don't have an answer to, but how do you control what you designed, and which then when it goes through to detailing and ends up in procurement, and which goes out to a bid? Because in all good faith, you can model your buildings, or as you do, and then develop the schema and work it right through to your detailing. But the products that you're picking or intend to use, I'm talking about embodied carbon now. It's not going to be for a year or more that they've finally procured. And then you sort of lose control over that when it goes out to bids. And so the question in my mind, and I don't know if you have any perspective on this, but how do you control that so that at the end of the line you get what you intended?
Well, it's interesting in Hastings, in the village of Hastings, I was co-wrote the Green Code, which was recently updated by a building scientist, and we are focused on materials and embodied carbon. And in it, it does require an EPD for the concrete. So the contractor is aware of that. So during construction, or to get the building permit, you need to provide that EPD for the concrete. And then the contractor has to prove that he followed those specifications. And you can't even get your final approval, your CFO, until the building inspector gets that document. Like the one when you showed of Byron Concrete. It's funny because that's one of the popular sources for concrete, and they do very well with making sure they're lower in carbon. But the building inspector was on the committee to write that Green Code. But this is a very small world, and that's one reason why I left the city, because there is more control in a smaller community, but I don't know how this can be controlled when you're working on a really large project. I don't know the answer to that.
I want to just bring forth a question from the audience, which is alongside this topic, which is when we are, let's say we decide to go forward with Passive House standards, even if we don't actually go for certification, but there is a lot more, and we talked about how less is more, but technically when you're doing Passive House, we're talking about, triple glazing, we're talking about more insulation, maybe double wall studs. So a lot of times this means like it's more. So like how does this impact the embodied carbon? Now we're having more insulation and more of lumber and all this stuff. Like how is this coming into the whole equation? And actually, there's an interesting question because I had this question last December in a New York Build panel, And it's obviously a question that a lot of people are concerned about when moving forward with Passive House, if it's really targeting everything.
Before you comment, let me
Go ahead.
let me do the attack. Okay, so because I don't have to deal with it. Okay, so no, I mean, so I learned a lot actually today about Passive House that I didn't know, and in a good way, I was happy to hear. However, I do know that, and again, maybe I'm thinking more net zero than the Passive House, but I mean, one of the trouble areas is insulation. And you also may throw in triple glaze windows to that too. When it comes to embodied carbon, because those are two standard go-tos, I guess I'll say in net zero. I don't know if it's in Passive House. And clearly, just from any engineering point of view, that you get to the point of diminishing returns. You know, you can't just keep packing insulation on it. The fact is, you get to a point where it doesn't really make much of a difference. So, you know, on the surface, that is a significant problem. And now I'll turn that over to you guys to handle.
See what I can do with this, and Christina, you can fill in. So, you know, it's an optimized building, and you're juggling a lot of different factors. There's a lot of programmatic requirements. If any one thing is driving it absolutely, you may make one set of decisions for another. You know, that said, sure, there's triple glazing, there's a bit more insulation, and, you know, maybe or maybe not there are more materials, because as you're optimizing the building with all of these programmatic requirements, including low upfront embodied carbon, you may be making slightly different decisions and bringing things together. One thing we see, I know windows are very fun to pick on. To be honest, it's an easy one with the triple pane. But what we see with energy balance and calculating and the thermal comfort is where projects can get into trouble is because they're cheaping out on the windows. And we need really high quality windows to make sure that we're getting the predictability that we need. And if we're doing a lot of insulation on a net zero or low energy, high performance building, whatever we want to call it, but we're not actually getting the predictable performance, the savings out of it, then, you know, that's a big loss. But if we're getting the savings and getting the performance out of some extra insulation, it can totally be worth it and totally make sense. So I think Passive House practitioners, you know, in the mantra of less is more, certainly look to follow that. And, you know, a big driver is things like surface to volume ratio and how optimized the orientation is, or the just the physical layout of the building. Reducing concrete is probably the biggest single thing that anybody can do, which has nothing to do with Passive House. I love the Miami School of Architecture example. And there's a lot of, you know, examples of folks undermining, you know, one set of goals with another. So it's totally possible. We can actually, with the insulation, have it be carbon sequestering and can make the buildings carbon negative. It's done regularly. So it's not an either or. It depends on the specifics of the project and the optimization.
Yeah, I agree with that, and it's not more and more. I don't agree with that concept of more and more, because this is a matter of optimizing the materials. So, for example, on a mixed-use building compared to a single-family building, you have much more floor area compared to the amount of exterior envelope. So, you know, your demands for insulation are much less, and you can use almost half the amount of R-value you can for a single-family house. But also the shape of the building that we design, that surface to volume ratio should be thought about in the very beginning of the project. So you don't have a very ornate building with lots of different, very long linear, and just, you know, it has to really think about surface to volume ratio when you design the building. And then, of course, optimize the orientation. You know, our Yonkers project, we might be adding clear story windows because we have so little south-facing glass, and we just barely meet the standard. But I think about that in design, and that's what we should all do to make sure we optimize the design of the building before we look at all the other ideas. You know.
Can I add one quick thing? So just to, maybe it's geeking out a little too much, but one thing that's specific, that's a huge driver of the ultimate performance, is the air tightness. And everyone thinks about passive house air tightness as it being such a huge obstacle, impossible to get to, it's unrealistic. But we see time and time again teams getting it, hitting it, and then after project, they can go tighter and tighter and tighter. And we regularly see teams going, you know, twice as tight, 3 times as tight, 4 times as tight. And the magic happens, which is happening in projects. It's easier on bigger projects, more difficult on smaller projects. But if you can dial in the air tightness and say you're going to be 25% more airtight than what the standard even requires, you can pull insulation off the building. You can do other aspects to the building that actually reduces the materials in the building using the same air tightness materials, no more materials than actually what code requires air tightness. It's just a pretty flimsy air tightness. Similarly with the ventilation units, you can have a relatively poor ventilation efficiency and require more insulation, require better windows, require a lot more work. But if you get a really great ventilation unit, it can really ease up on other things. So that's an example of trade-offs of scope that isn't necessarily, you know, one or the other.
Another thing to just, which points to this, the 5 materials that the Inflation Reduction Act money is going to, that was requiring now EPDs, you know, and to create the standard, are concrete, steel, glass, insulation, and asphalt. So, and it's all under the guidance of the EPA. And so those are the 5 big ones that they have identified as the real killers. And so, you know, the one that surprised me is I had no idea that insulation, that there's good insulation and bad as far as embodied carbon goes. And obviously, it is a big one.
Just for the final question here, we have a lot of actually really good questions. So I hope whoever didn't get their questions answered, they get to come to you in person and ask you. But for a final question, I'm just kind of merging 2 questions in one, which is someone who's just starting out and they want to know, like, where can I find a locally, you know, someone who can make windows for me locally? I don't want to get it from, you know, Dubai or, you know, China. So like, where is somewhere that they could get it locally, or where in terms of like modeling and energy modeling, where do they start? So these are like some questions of like, where can someone start? I know you mentioned some programs like 475, but where would you?
Well, go to the U.S. Department of Energy website and get the free model and try it out. And you'll soon realize you got to buy the professional model to get the climate data info that you really need to do a better model. About windows, I don't want to mention companies, but there are U.S.-made windows, because I went out of my way to get mostly American-made products for my own house. I couldn't get I still to this day find it hard to get an affordable passive house exterior door, but maybe Ken knows about where you can find these things.
Yeah, an exterior door is the final frontier, really.
I guess in Canada.
Well, yeah, I mean, the trick is to buy a window that acts like a door, essentially. But for a front door, it's not necessarily going to work. But there are more and more suppliers. There's a window company in New Jersey, right at the New York border, that's supplying certified passive house windows. I know some American manufacturers are getting close, although what they're typically producing are appropriate for warmer climates, not up here. You know, the availability from Europe is greater and greater, where there were, you know, options, just a handful of options a number of years ago. There are now dozens of options and suppliers. So, yeah, I would leave it there. I will maybe continue the conversation later, Bill. The thing about transportation, depending on where something's made in Europe and how it gets here, if it gets on a ship pretty quickly and you're in New York, that's much better than it coming from California. I'll leave it there.
I'm not going to go there.
All right, thank you so much. I hope